Calculus is the study of rate of change, instantaneous rate of change, or the derivative at a point, or the limit at that point, or the slope of the tangent line. So we really don't have any way of finding the slope of tangent line, but we would be estimating the slope of tangent line using the secant line by bringing the points really, really close to each other. So let's start by talking about average rate of change or average velocity. Rate of change or velocity, you might recall distance is equal to rate into time from algebra, the distance rate time formula. If you don't recall it, remember the word dirt. You will never forget this formula. Distance is rate into time. The rate or velocity is equal to distance divided by time, which is change in position divided by change in time. If we represent position function with the y, that would be delta y. Delta y represents change in y divided by change in time. So that change in y can also be written as y2 minus y1, difference in the 2y coordinates, divided by x2 minus x1, difference into x coordinates. If we represent the position function as a function of time, then that would be the y2 minus y1 over t2 minus t1, the difference into times. Okay, the average velocity is the slope of the secant line, which can be easily found by using the slope formula from algebra. We might recall slope of a line can be found if we know 2 points on the line, then difference in y coordinates divided by difference in x coordinates is the slope of the line. And we can find the average rate of change. So if I go from here to Sacramento and I know the distance traveled and I know the time taken, I can find my average rate or average speed at which I was going from here to Sacramento. But what if I want to find out exactly after 15 minutes or how far I was traveling after 20 minutes? If I want to find out the instantaneous rate, how would I find the instantaneous rate? That's where calculus comes to rescue. Instantaneous velocity or rate of change is the slope of the tangent line. So if you look at this picture carefully, I have a curve with 2 points P and T on it. The first point is x1, y1. First point has the coordinates x1, y1. The second point has the coordinates x2, y2. So if I were to find the slope of secant line, the line passing through the point P and T is called the slope of secant line, the line that's touching at 2 different points. So if you have a curve, I just want to distinguish that you understand the difference between a secant line and a tangent line. The secant line is, this is secant, and tangent line touches the curve only at 1 point. So secant line touches the curve at 2 points, tangent line touches the curve at 1 point only. So I do have a line with given 2 points with coordinates x1, y1 and x2, y2. I can find slope of secant line by using the slope formula, which is y2 minus y1 divided by x2 minus x1. What if I want to find the slope of the tangent line at point T? So if I want to estimate what is the slope of the tangent line at this point? So how do I find out the slope of the tangent line? What I can do is I can bring the point P really close, infinitesimally close to the point T, and I can bring the point P very close to T. That means infinitesimally close, very close to T, and then estimate the slope using those 2 points. So that would be again y2 minus y1, or I can name the coordinate. I can bring the point P here, and the coordinates can be x3, y3. Now we can estimate using the same slope formula. We would have our 2 points P and T really close now, and our slope formula would become y3 minus y2. Yep. Difference in the y coordinates divided by difference in the x coordinates. So that would be the slope of the tangent line. And again, that's our estimate. We brought the 2 points very close to each other and infinitesimally close to each other, and that would give us, then we use the slope formula to estimate the instantaneous rate of change. Here is another better picture. Here's my 2 points. If I want to find out the average rate of change, the secant line, slope of secant line will give me the average rate of change. If I want to find out the instantaneous rate of change at a point, I would bring 2 points infinitesimally close to each other. So I will be using these 2 points very close to each other and estimate the slope f of x2 minus f of x1 is same thing as y2 minus y1. Remember, f of x is same thing as y if y is a function of x. Okay, so same thing, the slope formula. So if you bring 2 points very, very close, we can find the slope of tangent line by bringing the 2 points very, very close to each other. So average rate of change is the slope of secant line, instantaneous rate of change is the slope of tangent line. How do I find the slope of tangent line? So I will have to bring the 2 points very, very close to each other. Galileo discovered that if object is released from time t equals 0 from a state of rest, the distance it travels after t seconds is given by s of t equals 4.9 t squared meters. So this is a formula, you should remember it. It will come handy sometimes when you're doing free fall problems and they don't give you the function. Then we can use Galileo's formula to estimate the distance traveled by the object if it's free falling from a height. Okay, an example number 1, a hammer falls off of a scaffolding at time t equals 0. Estimate the instantaneous velocity at t equals 0.8 seconds. Okay, so a hammer is falling off of a scaffolding at time t equals 0. We want to estimate the instantaneous velocity at t equals 0.8. So how do I estimate the instantaneous velocity? First of all, I don't know how much distance is the hammer traveling, but Galileo told me that if you have a free falling object, it's going to travel 4.9 t squared distance in t time, whatever t you're dealing with. So what we would do is we want to estimate the instantaneous rate of change. So that means we're going to find the velocity, instantaneous velocity. So we'll find the points very, very close to 0.8. And you might say which side. We would use points on both left side and right side. It's good to use both sides. Or let's say the time started at t equals 0. Okay, because it's a time, I'm not going to use, I'm going to start with 0.8 to 0.81 and 0.8 to 0.805. So you might say, who tells you to pick these values? Actually, no one. That's going to be the values. You want to pick the values, the 2 points. These are your T1, T2, or you can call them X1, X2. It doesn't matter because you have a function of time. Your position is a function of time. So I'm going to use a T1, T2. So these are your time intervals, and you're getting closer and closer to 0.8. Okay, we want to estimate at 0.8 seconds. So I'm picking the intervals closer and closer to 0.8. So to find the average velocity, it's going to be the slope, which is difference in y coordinates divided by difference in x coordinates. So s of 0.81 minus s of 0.8 divided by 0.81 minus 0.8. That's same thing as y2 minus y1 over x2 minus x1. If it's easier, you can think of this as 4.9x squared. So it might make better sense to you if you are more used to looking at x's and y's, but it's better to get used to, your any dependent and independent variables. They don't be stuck with x's and y's. So once we find s of 0.81, that would be that's change in position, which is given, and then change in time, which is given as well. And this is going to be, I think it is, let me check really quick. I think there's a typo here. 0.07889 divided by 0.01. That is, so there is a typo here. There is going to be a 0. So this is going to be 0.07889. Okay, 0.07889. So that was a typo here. Please ignore that. And that's going to be in meters. All right, so here we can find the average velocity for one interval. Same thing for the repeat for different intervals. Keep on getting closer and closer to 0.8. And when you are really, really close to 0.8, you do have a good estimate. So your average velocity will be 7.8 meters per second. 7.8 meters per second. That would be the average velocity. Okay, why am I choosing this answer? Why am I not choosing 7.889? If you want to be more accurate, let's go ahead and use 7.84. Okay, 7.84 meters per second. Again, why am I using this interval? Because this is the interval that is closest to 0.8. Okay, 0.8 and 0.8000001 are very close to each other. So I can estimate the slope of tangent line by using the slope of secant line. And these are my 2 points which are very close to each other. Okay, another example. A ball is thrown into air with a velocity of 40 feet per second. Its height is given by this function. And we are being asked to find out the average velocity for the time period beginning when t is 2 and lasting all these times. I'm not going to do all of these, and I might not even finish it all, but I will help you get started. So we want to find out the average velocity over the interval starting at 2 to 2.5, because it's starting at this and lasting 0.5 seconds, 0.1 second, and so on. So how do I find average velocity over this time? I will have to do s of 2.5 minus s of 2.0, or I don't need to write 0.0, s of 2 divided by 2.5 minus 2. And that 2 is really long. And that's going to turn out to be, use a calculator. I'm just going to plug s of 2.5. We're given the function s of t. So I'm going to plug the 2.5 in here. 40 times 2.5 minus 16 times 2.5 squared minus 40 times 2 minus 16 times 2 squared divided by 2.5 minus 2. And once you're done with this calculation, whatever number you get, that would be your average velocity starting between the interval 2 and 2.5. If you want to estimate the average velocity at time t equals 2, I would use the interval 2 and 2.01 because that's closest to 2. Okay, here's a table. I completed this step for all of these. So between 2 and 2.5, when I plug these into the calculator, it turns out to be minus 32. And between 2 and 2.1, negative 25.6. Between 2 and 2.05, negative 24.6. Between 2 and 2.01, negative 24.16. So what do you think will be instantaneous velocity at t equals 2? It is going to be the one interval which is closest to 2, and that's negative 24.16 meters per second. What tells me the units are going to be meters per second? The Galileo's formula is the time is measured in seconds and the distance is measured in meters here. All right, let's see one more example. Example number 4, estimate the instantaneous rate of change of this function at t equals 1. So what we can do is we want to estimate the instantaneous rate of change of this function. Well, it's a square root function. Let's go ahead and graph this really quick to see how does this function look. So I'm going to graph y equals square root of 3x plus 1.
2x minus
go to
5.
Desmos.
And that's the end of it because
Okay,
we were...
I don't want this. Desmos. Y equals square root of 3x plus 1, I believe. Let me double check if this is correct. Yep, 3x plus 1, and we're trying to estimate at t equals 1. So we're trying to estimate at t equals 1. I think this is where the 1 is. What is the slope of tangent line at this point? So what's going to be the slope of tangent line at the point 1? If I draw a tangent line at the point x equals 1, what's going to be the slope of tangent line if I draw a straight line or tangent line at this point? That's what we're trying to estimate. Graphically, I have no way of finding, or I can tell that it's a positive slope. That's all I can tell, but I don't have any way of estimating. What I would do is, graphically, if you want to estimate, you can find 2 good points and then use those points to estimate. And it's better if the points are really close to the one you're looking at. But numerically, there is a better way of doing it. Let's take a look. What I would do is, because I want to estimate at t equals 1, I can pick several intervals. I thought it's a highlighter. Several intervals closer and closer to 1. So 1 to 1.01. What's the average rate of change? How do I find the average rate of change? So over the interval 1 to 1.01, I can find the average rate of change by using y2 minus y1 minus x2 minus x1. So it's going to be f of t2 minus f of t1 divided by t2 minus t1. And my t2 is going to be 3 times 1.01 plus 1 minus square root of 3 times 1 plus 1 divided by 1.01 minus 1. And when I plug it into the calculator, I'm going to get that. And I repeat this process with different intervals. And finally, because I want to estimate at t equals 1, I want to pick the interval that is closest. And looking over here, the interval that is closest is these two intervals. Coming from the left and right hand side, these intervals are really, really close to the 1. 1.00001 and 0.99999 are very, very close to 1. So we can use these points to estimate the slope of tangent line, although we are using the slope of secant line. But because my points are very, very close, we can estimate the slope of tangent line, and that's going to be 0.75. And what are the units? Because my function didn't have any units, so I'm not going to use any units here either. That would be all for now. So remember, we will be using the slope of secant line to estimate the slope of tangent line. The slope of tangent line is also called instantaneous rate of change. Slope of tangent line is also called derivative. Slope of tangent line is also called limit. So that's where calculus will be revolving around. Another big part of calculus is estimating the area under a curved surface. We will talk about it later in the course.